Alright, so we're moving on to section 4.4 and 6.4, which is solving trig equations. It says here that the unit circle in combination with the ideas of identities can be used to easily solve seemingly complicated equations involving the circular functions. Factoring is also a useful skill when solving equations involving circular functions. Now there are some steps given on your page. Just quickly read through them. Step 1, if just sine, cos, or tan, then you isolate and use the unit circle to find the solution. So the solution in these cases, you guys, is the angle. So we're always going to be looking to find the angle of whatever equation you're dealing with. If you have sine squared or cos squared, then set it equal to 0 and factor. Just like if it's quadratic, right? Anytime you see a squared, you set it to 0 and factor. You also have to pay attention if you're asked to provide a general solution or a particular solution. Now, a general solution is basically where there's no domain given, so you have to put the plus 2 pi n at the back, which means that it could keep making loops around and getting back to that spot. But if it's a domain that's given, you can just list your answers. So that's the big difference between general and particular. Let's try a couple. So our first example, we're solving over the domain of 0 to 2 pi. So we're solving it within one full loop. Notice that both 0 and 2 pi are included in the domain. So our first question is 2 sine theta minus 1 equals 0. So since the sine is not squared, we're just going to try to get sine by itself. So to get sine by itself, I'm going to add the 1 to the other side. So we get 2 sine theta equals 1, and then divide out that 2 from the front. So sine is half. So now we're going to look on our unit circle, and we're going to find all the places in radians where sine equals half. So when I look here, I see that sine is half at pi over 6. Sine is half over here again at 5 pi over 6. But then in your other places where sine is half, it's actually a negative, so those wouldn't be included. So there's only 2 places on your circle where sine is half, and that's at pi over 6 and 5 pi over 6. So we write theta equals pi over 6, comma, 5 pi over 6. Oops, 5 pi over 6. To represent the places on the circle where sine was half. So here when I combine like terms, I'll put the 3 sine subtracted over to the 5 sine, so we'll get 2 sine theta. And then if I subtract my 2 over to be with my 1, it's at a negative 1. And when you divide out the 2, we'll get a negative 1 over 2. Then when we look on our circle, you should find the angles where sine is negative half at 7 pi over 6 and 11 pi over 6. So looking at example C, sine squared minus sine equals 0, I see there's a squared. Now you guys, when there's something squared, this is like something quadratic. So anytime there's a quadratic, you should try to factor it. So for this one, I see that sine is common to both of these. So I can factor by dividing out a sine to the front. If I divide sine squared by sine, I'm left with sine. And if I divide negative sine by sine, I'm just left with minus 1. So again, all I've done here is divide sine to the front, which means factoring out the GCF. Now I've got 2 possible options. So when it's a quadratic, remember that you set each factor equal to 0. So I'm going to set sine theta equal to 0, and I'm going to set sine theta minus 1 equal to 0. And this sine theta minus 1, I still need to move that around because it's not quite sine by itself. So if I add the 1 to the other side, we get sine theta equals 1. So on your circle, there's 2 different things now we're looking for. On your circle, we're looking for where sine is 0 and for where sine is 1. So my options here for sine is 0 is that theta could be at sine is 0. Okay, here sine is 0, and here sine is 0, but then also at 2 pi, it's 0 again. Because remember, you're taking one full loop, including 2 pi. So we'd say that it's at 0, pi, and 2 pi. So theta equals 0, pi, and 2 pi. On the other side here, where sine equals 1. Sine equals 1 right here at pi over 2. So for this one, theta equals pi over 2. So we actually have 4 answers altogether for the solutions of this equation. Alright, question D says that tan squared minus 5 tan theta plus 4 equals 0. Now you guys, again, I see a squared, so I can factor this. But think of this as x squared minus 5x plus 4 equals 0, right? Again, you can pretend that your tan is what your x is that you're looking for here. So this is just a quadratic, and when I factor it, I'm thinking two numbers that add to get to minus 5 and multiply to get to positive 4. So we'd have x minus 4 and x minus 1. So what this actually means, though, is that tan theta minus 4 equals 0, and that tan theta minus 1 equals 0. Because remember, it wasn't actually x that we were talking about, it was tan. So I've factored it. I've got tan minus 4 equal to 0 and tan minus 1 equal to 0. Now tan needs to be by itself. So we can just add that 4 and add that 1 to the other side. So we get tan theta equals 4 and tan theta equals 1. Alright, let's take a look at tan theta equals 1 first, because I think that's the easier one. Tan theta equals 1 on our unit circle. Now if we look at our unit circle, tan is 1 wherever your sine and cos are the same. That's because you divide sine by cos, so if they're the same number, you'd get 1. So we know that tan is 1 at pi over 4. We also know that tan is 1 down here at 5 pi over 4. Again, that's because both your sine and your cosine are the same. So I have two answers for that one. Pi over 4 and 5 pi over 4. But the other side is a little bit trickier, because the other side, we have tan theta equals 4. So, if you remember back to section 4.1, you can still get an angle by itself if it's not on the unit circle. You just have to use the inverse tan button on your calculator. So if you go inverse tan of 4, and here your calculator has to be in radians, because the question wants an answer in radians. Remember that this gives you your reference angle. And when I type it in, I get approximately 1.33. So if our reference angle is 1.33, I'm going to be looking either in quadrant 1 or in quadrant 3 for our angles, because that's where tan is going to be a positive number, so it's a positive 4 here. Positive. So this angle, if my reference angle is 1.33, that means in quadrant 1, I would also have a standard position angle as 1.33. So we'd say here that theta equals 1.33, that's in quadrant 1. But in quadrant 3, that 1.33 would go there. So how do I calculate the whole way around to that part? You add pi, right. The reason I'm going to add pi is because pi would be the 180, but then I have to go a little bit past pi by 1.33 radians to get that value. So for the other value, if I go 1.33 plus pi, I'm going to get 4.47. And so those are, again, my answers in radians. They are approximate because I had to round them for tan equals 4.